All right, we're gonna go ahead and get started. There should be a sign-in sheet floating around. Just make sure you sign in before you leave today. So this week you should have covered Newton's second law with polar and path coordinates, and then also work and energy, and then the conservation of energy. So we're gonna do a few problems from both topics. Is there one in particular that you'd like? Would you rather do polar and path with Newton's second law to start, or would you want to do work and energy, or does it not matter? We'll do both anyways, but is there one you want to start with? No? Okay, we're going to start with polar and path coordinates then. All right, so I don't think this problem was posted, but we're going to do this one. This one might be like, I pulled from some of the problems that are supposed to be a little more similar to your homework, and maybe those will help. I don't know if they are similar, but I tried to make them a little bit more similar to your homework. Okay, so in this problem, we have a sphere in a dish the dish is rotating around the vertical axis. And we want to find out the velocity of the sphere and the magnitude of the normal force exerted by the sphere on the inclined surface. So the sphere is at rest relative to the dish. So the sphere itself is not moving, the dish is moving around the vertical axis. So we're going to start with a little bit of geometry, algebra, to find some of the things we need to know. If we want to find the normal force, we need to find the, well, first let me start with, like, we're talking about polar and path coordinates. So that would probably give you a hint that we're either going to use polar or path coordinates here. If we need to find the normal force on this sphere, we need to find the force that's acting this way, or normal to the sphere. That is, again, another hint that we might be using, like in this case, as you can see, we might be using path coordinates, because path coordinates, we have one coordinate going towards the normal, and then one going tangent to the motion of the object. So we need to find the angle of the slope of this bowl, exactly where the sphere is sitting on it, so that we can find the normal force. So the parabolic curve of the bowl is given by y equals r squared over 6. So if you remember back to like Calc 1, to find the slope or the tangent of that parabolic curve, the tangent line of that parabolic curve, we need to first start by taking a derivative. So we need to find the slope exactly tangent. That was not very tangent. There we go. Exactly tangent to the point on that bowl. Okay. So if we know that y equals r squared over 6, and we want to find the slope and then the angle of the dish at that exact point, we can say that tan theta is equal to dy over dr. So we're basically just trying to find that angle of the slope, which is the derivative of our parabolic function. So the derivative of y is just going to be 2r over 6, or r over 3. And we know exactly what our r is at this point. We know that it's 3 feet. So we can go ahead and plug in 3 feet. So we have tangent of theta is equal to 3 feet for 3. And that gives us tan theta equals 1. And the angle that gives us tan theta of 1 is going to be 45 degrees. So then we know that this sphere is resting on a 45-degree angle surface at that point. So now that we know that, we can start to draw our free body diagram. So the only things that are acting on this sphere at this time are its weight and then the normal force. And so if the ball is resting on a 45-degree angle, the normal force is going to be acting normal to that 45-degree angle slope. So normal there. And then we can do some more geometry to figure out what angle that's going to be at. So if we draw a straight line as if it was the y-axis down, and we know that this is 45 degrees, then this is also going to have to be 45 degrees from the y-axis. So we can say that the normal force on the ball is acting at a 45-degree angle. Okay, so those are the only two forces we have on the ball. Then we can start to sum up our forces. Oh, and let's draw a coordinate system. So we're going to say that our y direction is that way, and then we're going to use an n that way. And then we need to figure out we should draw what direction the acceleration is going to be. So the sphere isn't accelerating with respect to the surface itself. It's just accelerating with the surface, and the surface is spinning. So we're going to have some center-focused or centripetal acceleration going this way. So it's going to be m, a, n, if we're following that coordinate system over there. All right. So now that we have our free body diagram and we have our acceleration drawn, we can go sum up our forces. So we're going to start in the y direction because we don't have any acceleration there, so that'll be easier to solve first. So if we want to find the components in the y direction, we have that'll be n cosine of 45, and that's pointing upwards. So n cosine 45 degrees, and then we'll subtract the weight because we're going in the other direction. So that's mass times gravity. And then we end up, and then that's just going to equal 0. So we can leave that there. Let's solve for n, or let's get it set up so we can solve for n. So we'll have mg divided by cosine 45 degrees. Okay, And then let's sum up our forces in the other direction. And that's going to equal mass times our acceleration, our centripetal acceleration in the n direction. So here we again have the other component of the normal force. So that's going to be n sine theta, or 45 degrees. And since we have going that way as our positive, or going to the left as our positive, then we can keep that as a positive. And then that's just going to equal our mass times acceleration in the n direction. Okay, so then we can go ahead and start to solve for our components. We need to know we need to know our velocity. Yeah, it says determine the velocity of the sphere. So our velocity of the sphere, because we're talking about an angular acceleration, it's going to be v squared over r. So we're going to plug that in for our an, and we're going to substitute in this for the n there. So we'll have that mass times gravity is over cosine of 45 degrees is equal to mass times velocity squared over r. And then we can, oh, I forgot the sine term. Whoopsie. We need to put that, we need to put this sine term in here as well. So sine theta, and then m times v squared over r. Okay. So we can simplify this down. Sine over cosine is going to equal tangent. So it would be mg tan of 45 degrees equals mass times velocity squared over r. We can cross out our masses, and then we're left with velocity squared is equal to r times the acceleration due to gravity times the tangent of 45 degrees. So v squared is going to equal our 3 feet times, since we're in feet, we're going to be using 32.2 feet per second squared as our acceleration, or our gravity. And then the tangent of 45 degrees is 1, like we set up there. So this is just 1. So we get v squared is equal to 96.6 feet squared per second squared, and then velocity is equal to 9.83 feet per second. Okay. So that's the first part. The next part asks if we can find the normal force. And that's not too difficult because we know the mass of the sphere, and we know the weight of the sphere, and we have this equation, so we can just plug it in for that equation. So n is going to equal the weight of the sphere, which is 2 pounds, divided by cosine of 45 degrees, and when we do that out, that's going to be 2.83 pounds. All right. Any questions about that one? Anything you want clarified? All right. So here's our next problem. I'll give you a second to copy it down, make a sketch, whatever you need to do. Okay, so for this one, we have a block that's inside an arm with a slot, and the arm is held on a. It can pivot around a point, and then the block can slide without friction through the slot. So we know already that we're given already that the rod has a constant angular acceleration. So right off the bat, we're given theta double dot, which should immediately say we're in polar coordinates because that's the acceleration in the theta direction for polar coordinates. So we know we're going to be talking about polar coordinates. So we write down that we have a theta double dot of 10 radians per second squared. And then we're given that when theta is 45 degrees and r, meaning the length up from the block to the pivot point, is 0.8 meters, that the velocity of the block is 0. So at that specific instant, we need to determine the force exerted on the block by the arm, and then the relative acceleration of the block with respect to the arm. Okay, so let's write down some of the things that we can infer from what the problem says. So we're given that the velocity of the block at this point is 0. So that means the velocity in the radial direction is 0, so our r dot is equal to 0. And then that also has to mean that the velocity in the theta direction is going to equal 0. So our r theta dot is going to equal 0. But we already know that we have an r of 0.8 meters. So because r isn't 0, then our theta dot is also going to equal 0. So let's start by drawing a free body diagram. So we're going to draw a free body diagram of just the block. And we know that the block is at a 45-degree angle. And the normal force of the block is going to be normal to that 45-degree angle. So that would be here. And then the weight of the block is going to be downward. And then when we put that into polar coordinates, and we think about the acceleration, we're going to have some acceleration this direction or angularly, and then some in the radial direction. Okay, so then we can start to sum up our forces. So we're going to start with the forces in the theta direction. So we want to figure out both of these forces in the terms of in their components as far as the theta and r direction. So our normal force is just in the theta direction, right? It's acting normal to our to our arm, which is in our radial direction. So we know that we're going to have some normal force in that theta direction, but we're also going to have a component of this weight right here. So we can go ahead, and I like to sketch out the little components just so I can see them. So I know I'm going to have some in this r direction and then some in the theta direction. So, and we can also, and we know that the arm, which is going this way, is at 45 degrees. So we can say that this angle right here is 45 degrees.
Question.
Yeah.
Sorry, so if we have the end force in this direction and then the angle straight with the end is 45 degrees, isn't that going to mean that the other angle is 45 instead of the lower one?
Because we've made a right triangle here, both angles are going to be 45 degrees because we have... No, you're okay. No, I had to stare at it for a little bit too.
Stop laughing. I hear you already.
No, it is so... It's fine. I've done the same thing. So... it's okay. So we're going to... We can say that our weight... the theta component is going to be in the negative theta direction, so it's going to be minus because our arrow was pointed that way. And then it'll be cosine of 45 degrees, but it doesn't really matter. You could use sine too because both angles are 45 degrees. And then that's going to equal our mass times our acceleration in the theta direction, which if you go back to your equation sheets, you'll know that the acceleration when we're using polar coordinates is going to be r theta double dot plus 2 r dot theta dot. And up here, we've already said that our theta dot and our r dot are 0. So we can effectively get rid of this term and say that's going to 0. So then we're left with our, this for our equation. And the only unknown we have is our normal force. So we can go ahead and solve for that right now. So we have n is going to equal the weight times the cosine of 45 degrees plus the mass times r theta double dot. All right, so our mass was 0.5 kilograms. So we have a normal force. Our normal force equals 0.5 kilograms times 9.81 meters per second squared times the cosine of 45 degrees plus 0.5 kg, and then our R is 0.8 meters, and our theta double dot is 10 radians per second squared. All right. Yeah.
When you go up to theta dot, you say R times theta dot is equal to 0.
Mm-hmm.
In this case, on the previous one, when we find theta dot, can you go up a little bit, please? Thank you. So why is theta dot 0 when R is 0.8?
Because we know that there's no velocity in, that we are told that the block is at rest at this very instant. So if our velocity is equal to 0 and our R is already equal to 0.8, then our theta dot term has to be 0. It's just because we were told that there's no velocity. If there was a given velocity, it wouldn't be 0. But in this case, because we have no velocity, we can effectively conclude that theta dot is equal to 0. So then n, once you plug all that into the calculator, n is going to be 7.468 newtons. All right. So then the next thing we're asked is to find the relative acceleration of the block with respect to the arm. Okay, so we know that the block, or the arm, has a constant acceleration of 10 radians per second squared, and that's in the theta direction. And so the block being carried with the rod is going to have the same acceleration in that direction, but the block is also moving up and down in the slot, so it's going to have some other acceleration in the radial direction. So we're not really concerned with the acceleration in angularly because we know that it's at a constant 10 radians per second. So we just need to figure out what it is angularly because we know that the rod doesn't have an angular acceleration, or a radial acceleration, sorry. So we have the sum of F in the radial direction is equal to MAR. Then the only component that we have in the radial direction is this component of the weight. So we have that the mass times the acceleration due to gravity times the sine of 45 degrees is going to equal m times, and then if you look back at your equation sheet, we will know that the acceleration in the radial direction is going to be r double dot minus r theta double dot. Nope, it's r theta dot squared, sorry. So we already know that this term is going to be 0 because our theta dot is 0. And then we can go ahead and cancel out our mass terms because those are on both sides. And then we'll get that gravity times the sine of 45 degrees is going to equal the acceleration in the radial direction. And r double dot is going to be 6.937 meters per second squared. All right, and then that effectively answers those questions, or the questions that we were asked for this one. Any questions, comments, things I should clarify? Yeah? No, you're okay.
Is the gravity, when is the gravity negative?
It really depends on what we've considered positive and negative in our schematic up here. So because this component of of the weight is going in the positive r direction, because we've established, I didn't write our coordinate system, but we've established our coordinate system as such for this case, that the gravity is going to, the weight or the acceleration due to gravity and the acceleration due to gravity are going to be positive in this case. But if I had established it with the r going the other way, it would be negative. So it's all about where you're referencing it from. All right, so we're going to move on to some work energy and conservation of energy problems. Does anyone want more practice with path and polar before we move on? Okay, we're going to go ahead and start this one. I'll give you a second to write stuff down and draw a schematic. All right, so we're given a system with a collar on a rod. There's no friction. And then there are 3 springs attached to it from different pivot points. We're given that all of the springs are the same. They have the same spring constant and they're the same unstretched length. And we need to find where the maximum speed occurs and what the maximum speed is. We need to first, where do you think the maximum speed of the collar would occur? Any guesses? So the maximum speed is going to occur at the instant that the acceleration is 0. And that's going to happen. So if we have our 2 outside springs acting so let me just draw this real quick. So if our middle spring is unstretched, it is directly over point D. That means, and because these 2 are evenly spaced from the middle point, that means they're going to be at this very instant acting in different x directions. So this the x component of spring B, which is here, the x component of that force is going to be pulling the collar back in that direction. And spring A, the x component of spring A, is going to be pulling the collar in this direction. And because they are the same spring, they have the same spring constant, and they'll be the same length at that point. That means that there is going the x direction of the force is going to cancel out, and so there will be no acceleration along the rod at that point. Now there will still be force in this direction, but because the collar is on the rod and it's constrained in the y direction, there still isn't any acceleration. So the conservation of energy states that the sum of the kinetic energy, the potential energy, and the losses from 1 to 2 is going to equal the sums of the kinetic energy and the potential energy at point 2. So we are given information about the collar at this instant, and then we also know that our final instant where we're trying to calculate the maximum velocity is going to occur here. So this is going to be our state 1, and this is going to be our state 2. So if we start with state 1, we know the mass of the collar, or we know the weight of the collar. We know the spring constant. We know the length of the spring. We also know that the collar is released from rest. And that's important because that means, since kinetic energy is 1/2 mv1 squared, that since it's released from rest, we have no velocity, that term is going to be 0. So our KE1, you might use different letters depending on the class. I think some people use T for kinetic energy. It depends on your professor. So our KE1 is going to equal 0. So then, and we don't have any friction, so we can assume in this case that we don't have to worry about this term either. We don't have to worry about any work externally. So we just need to find, for state 1, we need to find the potential energy. So where is our potential energy coming from in this case? The springs. So and we don't have anything coming from like gravitational potential, because if this is our reference plane, and we never move from this reference plane, so we just have the springs to worry about. So we need to consider each spring, and we know that the potential energy for a spring is going to be 1/2 times the spring constant times the length that the spring is stretched, and that's squared. So we need to find that for each of the springs. So if we first start with, we're at state 1, so we start with spring BC, that's this one right here. We know that that spring right at that instant is 2 inches. And we also know that the unstretched length is 2 inches. So our delta S for spring BC is going to be 0. It's not stretched at all. So for spring DC, we need to find its length here, and we know both sides of this triangle, so we can do Pythagorean theorem to try to find the length. So for spring DC, we can do the square root of 2 inches squared plus 2 inches squared. And that's gonna, and then I'm gonna divide that by, that'll give us a result in inches. I'm gonna divide that by 12 so we have result in feet, because we're given our spring constant in feet, in pounds per foot. So it's just gonna be easy in the long run. So I'll divide that by 12. And we're gonna get 0.2357 feet. So that gives us the entire length of spring DC. But what we're concerned about is the amount that spring is stretched. We're concerned about the displacement of the spring. So to find the distance that's been stretched, we subtract the unstretched length from this value we just found. And 2 inches in feet is 0.1667 feet. And then that's going to be 0.0690 feet. All right. So then for spring AC, if we go back to our picture, that's going to be this length. We have both legs of the triangle. So Pythagorean theorem, the square root of 4 inches squared plus 2 inches squared, divided by 12. And that's going to be 0.3727 feet. And again, same thing, we need to find the displacement. So subtract the unstretched distance, and we get a delta S of 0.2060 feet. Okay. So now we can find the total potential energy at point 1. So PE1 is equal to the sum of 1/2 K delta S squared and our total potential energy there is going to be 0.7081 foot-pounds. Okay, so now we've taken care of state 1. Now we need to figure out the kinetic energy and potential energy at state 2. So the process for finding the potential energy, pretty much the same. We just have to find the delta S of the springs and sum them up. But this time we have kinetic energy, and that's how we're going to solve for our velocity. So we'll start with our potential energy again. We have that PE2 is going to be equal to 1/2 K times the sum of the delta S's squared. So this time, spring DC is going to be unstretched, so that delta S will be 0. And then we're going to have spring AC and BC, they're going to be stretched the same length, just in different directions. So for spring AC and BC, again, Pythagorean theorem, they are each displaced 2 inches in the x and 2 inches in the y. And so that's going to give us a length of 2.2357 feet, and then a delta S of 0.0690 feet. All right, so we can go ahead and solve for our potential energy at state 2. So our PE2 is going to be 1/2 times 30 pounds per foot times 2 times 0.069 feet squared, and that's going to give us 0.1430 foot-pounds. Okay, so the last thing we have is our kinetic energy at state 2. So if we rewrite our energy balance, we know that the potential energy at state 1 is going to be equal to the kinetic energy at state 2 plus the potential energy at state 2. So we have 0.7081 foot-pounds is equal to 1/2 the mass, which we're given the weight of the block. So I'm going to write this as weight divided by gravity, just so we remember, times the velocity at point 2 squared, and then times plus 0.1430 foot-pounds. So then we can solve for our v2 squared, and we get v2 squared is equal to 18.197 meters squared per second squared. V2 is equal to 4.27, I wrote the wrong unit, we're in feet, foot squared per second squared, feet per second. And that's our final answer.